Okay.
Homework, I think 7 and 8 were shell, so I didn't do them.
I'll have to look and see. It could be that I forgot to exclude them, or
Because it had like a x equals 7, and then use the x for the variable of integration.
it could be, and technically then, yeah. Okay, so, yeah, 7 and 8 are shell. I should have excluded those, and I overlooked it. They are shell, which technically there's probably another way you can do it, but it's not as easy, and you only had to write the integral anyways, technically. But, yeah, since we haven't talked about shell.
I just skipped those because I had no clue how to do them.
Yeah, rightfully so. Okay, so trapezoidal rule. We are looking at trapezoidal rule. It is a way to approximate an integral. Okay, so in those situations where maybe the integral is not doable, or whatever the case is, but it's a method used to approximate the integral. Kind of reminds me of how, when we first started solving integrals, before we actually knew how to do the fundamental theorem of calculus, when we would draw out all of our rectangles and stuff. When we first started, we talked about rectangles, and it could be, a left rectangle, a right rectangle, a centered, So the idea of the trapezoidal rule is that rectangles are somewhat accurate, but they're not exactly accurate along a curve. So the trapezoidal rule is trapezoids, which are more accurate because they could have a slanted edge. So it is based on the area of a trapezoid. I don't know how much you guys remember about the area of a trapezoid. 1/2, I always think 1/2 height times b1 plus b2. Here they have 1/2 b1 plus b2 times height. It's 1/2 times the sum of the bases times the height. Or the sum of the bases times the height divided by 2. Whatever variation you guys think of. Well, at least you realize that's a triangle. Yeah. Now, what we're going to use, and it's not in here, I'm going to write it out, but our variation on this for the trapezoidal rule is b minus a divided by 2n times y naught plus 2 times y1 plus 2 times y2 plus 2 times y3, so on and so forth, right? All the way up to y sub n.
Does it not have a 2 at yn?
It does not have a 2 at y naught or at yn. It's because those pieces would not be doubled. Okay. So, you might, once we draw this out, be able to see a little bit more of why it's y0, yn, but these have 2's and those don't. So we'll draw the first picture out, and I'll try and do some relations there for you. So let's look at example 1. Approximate the integral from 1 to 3 of x squared dx using the trapezoidal rule with n equals 4, and compare the estimate to the value obtained by using the fundamental theorem of calculus. So fundamental theorem of calculus, whether you realize it or not, would be evaluating that integral with how you already know. Okay? Just exactly what you're doing. But we're going to look at using trapezoidal rule. So the curve that we're talking about here is specifically what curve? Y equals x squared. On what interval? 1 to 3. So we're specifically talking about the curve y equals x squared on the interval from 1 to 3, which means I only need to draw the first quadrant curve. Okay, so there is my attempt at drawing the first quadrant parabola from 1 to 3, which specifically from 1 to 3 means we're going to be going from here to here, correct? And of course, we're trying to find the area of the curve there, the area under the curve. Now, n equals 4. Guess what n equals 4 means? We break this space into 4 trapezoids. Okay? So, if we think about breaking this into 4, I can split it in half there at 2, correct? And then officially, I guess I can ask you guys because you would know, but how wide is each interval here? 0.5, right? Because if from 1 to 3 it's a distance of 2, we're breaking it into 4 intervals, it's 0.5. So we're going to have 1, 1.5, which I'm writing as 3 halves, 2, 2.5, which I'm writing as 5 halves, and then 3. Now, officially, I should probably, we were able to pretty easily find that each interval would be 1/2 wide, right? In a more difficult problem, you could use the b minus a over 2n to find the width of the interval for you. So if I check that with you real quick, b minus a over 2n. What are b and a? 3 and 1. So if we say 3 minus 1 over 2 times n is the number of intervals, which was told to be 4. Well, 3 minus 1 is 2, 2 times 4 is 8. Wait a minute. Slight flaw in what I said here. How do we find the width of intervals previously? I threw in my confusion, my responsibility here. I threw in the 2 because I saw the 2 here. If you guys go back, when we would do this previously, if we were trying to find the width of the interval, I don't know if you recall or not, we just did b minus a over n. And I didn't glance over here at my notes too closely or anything. I just went with what I remembered. I saw the 2 here. I went with it. My apologies. And how did I know that I was wrong? Yeah, I was like, wait a minute. Why am I not getting... My apologies, folks. The 1/2 I was expecting. Sorry. That's when you're like, man, why isn't this working out? Where did I make my mistake? Okay. As we look at the formula up above, okay, we've already talked about we're going to know b and a, we're going to know n, yes? What we need to know are the y values, okay? And the y values that we're talking about are going to occur at the corresponding x values. So in other words, we're going to need to know when x is 1, what is that y value? When x is 3 halves, what is the y value? So on and so forth. When x is 2, when x is 2.5, and when x is 3. We're going to need to know each of those y values because that's what we're going to use to find the area. Okay? Now, if you want to do a chart, you can do a chart. Keep in mind, what equation are we plugging these x values into? Y equals x squared. Okay? We are, even though there are only 4 trapezoids, we are using all 5 pieces because think about it. A trapezoid is the bottom base and the top base added together, right? And so my trapezoid is standing on end, and so we need both sides of the trapezoid, so to speak. So if I plug in 1, I'm going to get 1. 1 squared is 1. What about if I plug in 3 halves? 9 fourths. What about when I plug in 2? 4. 2.5, or in other words, 5 halves is going to give me 25 fourths. And when we plug in 3, we get 9. So whether you put them on the graph, whether you set up a chart, it's whatever you need to do. But those are the y values we're using. And if we talked earlier how, is it going to make more sense now? The first and the last, we're only going to use 1 of. Each of the others we're going to use 2. Because if you look at this first trapezoid, it's the left plus the right. So that's this first one we're only using once. When we look at the next trapezoid, it's the left and the right. Well, this left is the right of the previous trapezoid. Does that make sense? And so that's why all the center ones are overlapping, because they're the left of one trapezoid and the right of another trapezoid. It's just the very first one and last one. Those are the pieces you won't need. Okay? So, let's fill this in. B minus A over 2n. So B minus A, we're going to do 3 minus 1. 2 times n is going to be?
Just the t equals 2 times n.
Yes. This time I do want the 2 times n. Unlike last time. Sorry. Okay. So there's your initial part. And this officially, notice the 1/2 in here. And what this is doing here, so think about it. The trapezoid is 1/2. You see the 2 in here, right? The height. The height of these trapezoids is the width of the interval. Each trapezoid has a height of 1/2. That is the B minus A over n. So B minus A over n times the 2 is the 1/2 times the height. And now we're just adding all these bases together. So, y naught, what is our first y value? 1. Plus 2 times the xy value. So 2 times 9 fourths. Plus 2 times 4. Plus 2 times 25 fourths. Plus 9. The last one you don't double. So 3 minus 1 over 2 times 4, 2/8, which is 1/4. If I clean this up, I have 1, 2 times 9 fourths, 9 halves, plus 8, plus 25 halves, plus 9. I still have a 1/4 out front, but 9 halves and 25 halves, so I mean 34 halves, and 34 halves is 17, plus another 8 and 9 is another 17. So now we're back at 34 plus 1 is 35, barring I did my math correctly. And 1/4 of 35? 35 over 4. Decimal answer is 8.75. I have both written down. Now, officially this said, compare this using the fundamental theorem of calculus. Is it going to match up exactly? It's not going to match up exactly because even though we're using trapezoids, are these trapezoids matching exactly with the curve? No. Closer than rectangles would, but not exact. Okay? So, I'm going to throw it right down here. Fundamental theorem of calculus. The integral from 1 to 3 of x squared dx. What do you get when you integrate? One-third x cubed from 1 to 3, which plug in the 3, we plug it in, 27 divided by 3, 9, minus 1/3, 9 minus 1/3, 8 2/3 is what part of my brain wants to say. I mean, it's whatever version you want to use here. Officially, we could say 27/3 minus 1/3 is 26/3. But if it's 8 2/3, that's 8.6 repeating. Is my answer similar?
Yeah.
It's in the ballpark, isn't it? So, again, remember, that's fundamental theorem of calculus right there, where you're actually evaluating an integral by hand. This was trapezoidal rule. Fundamental theorem of calculus is exact, precise. Trapezoidal rule, more precise than a lot of other estimations we've done, but still not there.
So when is like a time to use trapezoid thing instead of just taking the integral normally? Maybe because once you do it.
That's honestly part of my answer. I mean, I hate to give that type of answer, but that is part of my answer of, if they want you to demonstrate the trapezoidal rule. Now, if you look at the next problem, okay, this is one, well, see, we're going to have to use the calculator to be able to get this one unless we just leave it in terms of, like not actually have an exact worked out answer. But do you know what this graph looks like? Cosine x over x? I can cosine x. I can give you x. I can give you 1 over x. But cosine x over x? I can't really, talk to you there too much. So, if they worked something like that, where they provided enough information, you might be able to use it. And that's the other thing. Can you integrate cosine x over x? I don't think you could, unless there's something like with, I don't even think integration by parts would get you there. Maybe it could, I'm just not thinking of it, but. Okay, so. Is Daryl graphing it?
No, I'm playing around.
Well, we could go ahead. You want to go ahead and figure out how wide each interval is?
I was figuring out how much it would change the displacement, like 30 over versus 40 over distance on the 7th Street.
Really?
Yeah,
Really? That's what you're doing?
all I was doing.
Okay.
Because with the pointers, you're only allowed to have 450 cubic inches, so you could pour it 30 over, and you could just air 450, so you'd probably get by with it.
I'm going back to the trapezoidal rule. Okay. How wide is each interval going to be? Two pi minus 3 pi over 2 is what? Pi over 2. Pi over 2 divided by 4. Pi over 8. So each interval will be pi over 8 wide. Right? And technically you could probably do this without drawing the graph. But if I take a quick peek at the graph, now, I can go ahead and do like a Z-trig screen, but we really need a little bit, more than that. Specifically, what is our interval? So I can put in my mix, my x min, 3 pi divided by 2. You can just type that in as is. And it will convert it to decimal, which is fine, to 2 pi. Okay? Since my graph didn't appear to be going that high, actually that'll work. Nope, I should have. Okay. Since my graph isn't going that high, I should have changed my y min and max, shouldn't I? Because that's really hard to see. So it doesn't go very high at all. So how about I make my y min and max -1 and 1? I almost could have done more. Okay. So basically we just, in that particular section, we just have this big curve, right? Okay. I'm just going to sketch this piece of the graph in that.
It just starts to come down at the very end.
Okay. And it looks like, I haven't confirmed yet. It looks like at 3 pi over 2 it's 0. I didn't check that. But 3 pi over 2 to 2 pi.
It is 0 at 3 pi over 2.
Okay. Like I say, I would have gotten to that here in a moment. We're breaking this up into what? 4 parts. I said n equals 4, so 4 parts, so I can divide it into fourths. That's pretty easy. How far apart are these pieces? The width of each interval is pi over 8. I need these x values, don't I? I need these x values. So if we think in terms of pi over 8, what is 3 pi over 2 in terms of 8s? 12 pi over 8? You see where I'm going with this? Because I need those values, don't I? So if that first one is 12 pi over 8, and then each one is pi over 8 wide, what's my next piece? 13 pi over 8. 14 pi over 8. 15 pi over 8. And, does it work out? This is why I usually close the door, isn't it? Doesn't seem like it's that loud, but... We know it works out because 16 pi over 8 and 2 pi match, right? That's always good news. Okay. XY chart. My x values are what? All the ones we just listed, right? So 3 pi over 2, 13 pi over 8. I listed as 14 pi over 8. You could reduce if you wanted to. 15 pi over 8 and 2 pi. And I'm plugging these into what graph? Yeah, this is all about cosine x over x. Now, based on this is eighths and stuff, these are not pieces we know, are they? I can't tell you. I can tell you the cosine of 3 pi over 2, but I can't tell you the cosine of 13 pi over 8. So you're going to need the calculator. Okay? Now, while we're there, cosine of 3 pi over 2 is 0. And then when you divide by anything, it's still going to be 0. And then I would say cosine of 13 pi divided by 8 in parentheses. You guys can't even see what I'm typing. And then I'm going to have to divide by parentheses 13 pi divided by 8. And I have this lovely number here, yes? Now, depending on the situation, you can round it, or you could just grab this from the calculator when we need it. For my XY chart, just having something on my paper, I'm going to go for those 4 decimal places, 0.0749, but 6 tells the 9 to go up, and so it becomes 0.0750. Now, if I want to be lazy and don't want to retype all that into my calculator, I'm going to go up and copy. And then my 13s, I'm going to change to 14s. 0.1286. I'm going to copy and paste again. I'm all about you guys will find the lazy man way, right? 0.1568.
I think we could do this easier with computer programming. I think we could just put the boundaries and hit it once, then it run the program.
On this next one, it's going to end up being, if I do cosine of 2 pi, which you guys can come up with cosine of 2 pi, cosine of 2 pi is going to be 1, but then you have to divide by 2 pi, which, so you can put 1 over 2 pi, or what is 1 over 2 pi as a decimal? That lovely number. 0.1592. Okay. Let's set up this equation. T equals. What am I putting in for B minus A? Okay, 2 pi minus 3 pi over 2 divided by, not just 4, 2 times 4. It's 4, or 2n, so 2 times 4. And I'm going to take several rows to do this. Okay, what's my first y value? 0. And then plus, what do I do next? 2 times the next y value. So 2 times 0.0750 plus 2 times the next one, 0.1286 plus 2 times 0.1586 plus, what about the last one?
Wait, shouldn't that be 6.8 instead of 8.6?
Oh, yeah. 6.886. I got a little dyslexic along the way. I would love to say that's the worst mistake I make today. I'm doing well, but I already made a worse mistake than that one, so. Okay. At this point, it has to be a calculator, right? So, 2 pi minus 3 pi over 2 is pi over 2 divided by 8. So that's going to be pi over 16. I can do that part in my head. Stuff in parentheses I can't do in my head.
Really?
I can tell you what I have written down. I'm assuming it's right. I have written down 0.88. So then when you multiply that by pi over 16, I have written down 0.1728. So, interesting enough, if I run the integral on my calculator, because I'm not integrating that by hand, the calculator answer for fundamental theorem of calculus is 0.1758. And we got 0.1728. Pretty close. Okay. I probably need to double check for shell. I only have one that changes though, and that is 8 becomes 7 from 93. And 6 CD is something we'll be skipping. I can't remember what it is till I look at it, but I know it's something we need to skip. Obviously, because I have it written down. But.
I think my calculator doesn't like whenever I multiply a fraction by 5 on top.